There we go.
Thermo.
So what?
Let's talk about thermo.
Yes, I've prepared something
Ooh.
Lovely.
because Dr. Z told me to go over this.
Okay.
The Carnot cycle, which they talk about in class,
Yeah.
but I can talk about it again.
All right.
Go for it.
And then there's other cycles, but they're kind of all the same. They're all the same in that they all look very similar, and they're actually mathematically kind of all the same. And that'll be sort of the conclusion to this little.
Trip you're about to take us on?
Yeah.
Okay.
There, thank you.
I got your back.
Sounds like something I would say. So these are all done. All heat engine stuff is done on PV PV diagrams like this, P over V, right? And they're all with ideal gases. So let's just, for assumptions, we know that these are ideal gases. And therefore, so what does it mean to say it's an ideal gas? Like, how do we use that mathematically? That just means that PV equals nRT, or whatever I think it's that. Yeah, little n is the moles, right? It doesn't actually matter. NR are never going to change in this. And actually, in all of these, oh, sorry, there's another assumption, which is that it's a closed system. So the two assumptions are that I should write heat engines. So the two assumptions are that there's an ideal gas and that it's a closed system, and it's not an isolated system. So in the class that I was teaching about this, I was like, I couldn't remember the words for it, but I remember now, which is that a closed system has heat being transferred in and out of it, of course. That's the whole sort of point of these, is that you're transferring heat and then extracting work out of it. It's not an isolated system would mean that you couldn't have any heat transferred in and out, and the energies, the total internal energy is preserved the whole time. That's not what we want, because then nothing can really interesting can happen, right? But it's closed, meaning that N is constant, and M, which is like the mass, which we don't. I'll show you. The only reason I'm saying M is constant is because when we use this, delta E equals change in internal energy is mCV. This is the MCAT thing. So this is the change in internal energy for any ideal gas is always proportional to the change in temperature with this the mass of, right, so this is the one we use for the ice and water, that kind of, yeah. So we use the mass and this C. Now I'm putting a V now, which we didn't put before because that's the only one we ever care about. There's also another one called CP. This just means at a constant volume, but this is the one we always use. So I'm actually going to erase M. That doesn't mean we're getting rid of it. It just means that we're just, okay, so I guess you could just say that we're using C as the heat capacity, right? Because MC is just the heat capacity. And so in most of these problems, you'll see that it won't matter anyway. Nothing will compute matters for the amount of gas. And the amount of gas is N, and the mass of that amount is, you can just figure it out, it's a function of that, M, and those are both constant, and therefore NR is going to be a constant number, so this is just a number. You could also put capital NK if you want, obviously it's the same thing, and then M is going to be constant. So those are the assumptions we're doing when we do heat engines, okay? So heat engine is not something, if you're talking about a system, and you totally could talk about a system where you're adding more gas, like let's say you're doubling the volume by like pumping in more gas, and then you might have to use PV equals nRT to do other things like that. It's still, this is still true for any ideal gas, even if N is not constant. But for all these problems, these are going to be constant. And so really, like, there's three variables. There's P, V, and T, okay, in heat engines. And they're all related through this equation. So in some sense, it doesn't sound mathematically that complex. Like, there's not, like, a differential equation anywhere in here. There's not there's not weird random functions. It's pretty much just this, okay? Now, obviously, it doesn't mean the problems are going to be easy, but at least we know that the only variables we need to worry about are these three. Okay, so that's it. So now a Carnot cycle is just one example of a heat engine. And a heat engine you can describe by, now of course you can describe it in words by saying compression happens this way, blah, blah, blah. But you could just draw it on the PV diagram. So I'll draw this pictures. This is 1, 2, 3, 4. I'm just labeling the sort of vertices of this, and the vertices are like states. So each vertex describes, each vertex has of course, a value of p and a value of v. That's what defines them. And if it has a value of p and a value of v, it necessarily has a value of t. You can just compute it, right? And now, if I just draw it, you don't, because we don't know the scale, we don't really know these things. They would have to describe to you in any like problem. They would have to tell you what these curves are. Because if you just draw a curve if you just draw like a random curve here, that's describes something. That's just saying that you're, putting pressure and changing the volume of the gas. That's fine, and changes the temperature. That doesn't mean anything by itself. You have to, you have to know exactly what this curve represents. And in the Carnot cycle, so now we're actually picking an actual specific cycle. In a Carnot cycle, 1 to 2, which is this one, is isothermal, and 3 to 4 is also isothermal. Actually, I should have written that. Sorry. And all that means is that if we go now this is going to be our math. Well, okay, fine. Well, actually, I'll just draw a little. This is where I was going to draw equations, basically. But if PV is, now if it's isothermal, this side is a constant. In a P over V diagram, this is, of course, just P is a constant over V. This is constant over V. This is just like a 1 over X diagram. So, 1 over X, Y equals 1 over X looks like this, right? Of course, this side is negative volume and negative pressure, which doesn't make any sense. So we don't actually have negatives here. So anyway, it's basically that's why isotherms look like this. So this is an isotherm. PV is constant. So that's those two. Now, of course, if you change the constant, so this is just, this is like Y equals 1 over X, but then Y equals 2 over X. What does 2 over X look like? Well, if 1 over X is like this, 2 over X is like maybe like that or whatever. Maybe it's smaller. Whatever, it doesn't matter. The point is that you could put any number here and you'd get something that looks roughly the same shape. You could get it to be kind of really squeezed in, but it has roughly this shape. So all the isotherms look like this, and they all have different temperatures. That's the whole point, is that this number on the top is nRT, right? So isothermal, and this one, because it's higher up here, it has to be hotter, right? Because if all the points on this isotherm have a value of P times T, is, it's basically P times T divided by this constant is the temperature, right? These values are all higher P times T because they're sort of higher up, right? And these values are all lower P times T. So these are both isotherms, but this is clearly a hotter one. So we can call this T hot and T cold. So I'm just literally, these are the values of the temperature they have. Okay, so then, again, this is just the definition. This is still the definition of the Carnot cycle. From 2 to 3, these are adiabatic. And 4 to 1, there's adiabatic again. Adiabatic. Which just means that Q is 0. That means that there's no, well, it does mean that Q is 0, but it also means that delta S is 0. That's actually more sort of the true definition. Right? Adiabatic literally by definition means that the entropy does not change. So, yeah. So now what's actually happening? So okay, this is all just a graph, right? But what's actually like happening in this engine, like what would it actually, there's another diagram you could draw, which is not sort of a mathematical diagram, but it's just how people draw it. There's a heat, like bath, they call it, thermal like bath. This is how they normally draw it. So this is some ideal gas, right? This is a place where there's just, it's just a huge quantity of hot things. In other words, when you put the gas here and it warms up, you don't want this to cool down to, like, you don't want it to be one of those problems where you figure out how the equilibrium, this is just an infinite sea of hot, it's called a hot bath or whatever, right? And it has some temperature, and this is a cold bath. And what we're gonna do is, so this is physically what's happening, we're gonna take our can or whatever of gas, and we're gonna, well, it's not really a can, I guess it's like a piston, because we can see that the pressure and volume is gonna change the whole time, so it's not sealed or anything, it's like you can expand it. But then we're gonna move it over here, it's gonna pick up some hot, it's gonna heat up to a hot temperature, then we're gonna let it, so okay, let's actually figure, so this is one, let's say it starts at 1, and here is from 1 to 2, what's actually happening here? Where is it here? Well, 1 to 2, it's at the hot temperature. So it's actually started right here, and it's at the hot temperature, and it's absorbing some heat, right? Then from 2 to 3, we bring it back. It's going to cool down because remember this is T hot. This is T hot, so clearly it's cooling down because it's going lower. That's here where it's adiabatically expanding. We can see it's expanding because the volume is increasing from 2 to 3, and the pressure is decreasing adiabatically. So no heat is transferred because it's not in any of the baths. Nothing's happening, right? It's just adiabatically expanding. And then from 3 to 4, we bring it to this cold bath. Actually, sorry, from 2 to 3, I guess it's in the cold bath. And it's adiabatically expanding. Yeah, sorry, it's in the cold bath. Anyway, from 3 to 4, it's because I just mean because it clearly had to cool down. So how did it get to this temperature? But okay, put it in the cold bed. Then it stays here, stays at the cold temperature, but now the volume decreases. It contracts in this one, right, and releases heat, right. And then from 4 to 1, we go back here and it heats back up again. So this can of gas with the piston or whatever is just being moved back and forth between here. And the piston is being pushed right out and in. The volume is changing. So the piston or whatever is being pushed out and in. That's the work you're getting out of here, right? Because you can use that. It's a force times a distance, right? Because it's moving a piston, you know, right? So that's the work you're getting out of it. So anyway, right. And so now, if we want to, now the main thing you'd want to compute with this type of heat engine is called the efficiency. So they usually use eta. Sometimes they use a little e, but let's just use the, well, it depends. Anyway, eta is for efficiency. And this would just mean, so remember, we're talking about how heat is going from here to, we're saying that if we take heat from this to this, and we extract some work, can we extract like all of the work? In other words, does all of the energy we're moving sort of get extracted out as heat, or does some of it get dissipated? And you might expect the answer, of course, is that it's not going to be perfect, but it's not even like an engineering answer. Like it's not like a, well, you can, in this ideal world, it actually is completely efficient, but in the real life, it wouldn't be. It actually, in this ideal world, it's actually not completely efficient. And that's because of the other place where you, well, it's because, maybe I'll save this for later. It's because of entropy is the answer. And we'll see, we'll see, we kind of go through it in this derivation a little bit. So the definition of the efficiency is going to be the work divided by Q hot. And this is literally, it's just because the work you get out of it is the good thing. And how much does it cost you? It's the heat that you've taken from the hot reservoir, right? So imagine if efficiency was 1, which is of course the highest, it would be all of the work was, if all of the hot the heat you get from the hot bath was transferred to work, that would be perfect efficiency. That, of course, makes sense. So it seems weird that we don't have like a Q cold here, because heat is moving into this Q cold, right? It could happen in our diagram, but we don't have that anywhere because it doesn't really matter for the efficiency. Efficiency is just the work you get out over this, and yeah, and so during this phase, when it's in the hot bath, it's gaining this heat, Q hot, right? The gas is gaining this heat, Q hot. During this part, the gas is losing this heat, Q cold. And during, probably. And during this part, I think, this is W. Why is this confusing to me? The point is that we're supposed to get that. Okay. So, the only places where energy is being transferred anywhere in here is that heat is coming out of here, heat is going into here, and work is coming out of here. So by the first law of thermodynamics, the change in internal energy only comes from the change in the work done and the change in heat. And so we know that, this is here, the work done must be Q hot minus Q cold. Because just by conservation of energy, the Q hot, which is where all the energy is coming from, is going into two places. It's going into Q cold, heat transferred away, and it's going into work, right? This is Q hot incoming. Coming out is work, and coming out is Q cold. So this is literally energy conservation here. So that's how I know that. What's that?
The difference is the work.
Yes, the difference between this is the work, right? And now, okay, now I could have this expression. Now you could see that, well, actually, let's just divide them. So we just get 1 minus Q cold over Q hot. Now, actually, this kind of makes sense already. If we didn't, heat is a weird thing to imagine. So, but this is actually kind of a good answer, because this just says the efficiency is perfect minus this sort of correction. And the correction is based on how much Q cold there is. And if there was no Q cold, then all of the energy would go here, and we would have perfect efficiency. Okay? Now, that doesn't really actually tell us much about, okay, that's fine, but what do you do in the system to make Q cold different? Like, how do you know, like it seems like these quantities Q are not really up to you, and this work is not really up to you. You just put what you're doing is you're putting gas in a compressible thing, a container with a piston, in a hot place and then in a cold place, and that's all you're doing, and you're just extracting the work from it. How would you make it more efficient? Like, how would you make Q cold a different thing? These are not very good variables to leave it in terms of, because they don't really tell you much about what to do about it. These are sort of internal thermodynamic variables. We want to take it in terms of like the input variables, like these things. So what you could do is say that Q hot is actually equal to, so the heat so remember how we know that work, okay, I'm going to write a bunch of equations here. So energy, I already wrote this up here, but is CV delta T, that's the total internal energy. We know that this is Q minus W. I'm not writing these because they're all relevant right now. I'm just writing them because they're the thermodynamics equations. Work is roughly P dV, integral of P dV. Now, normally, we might not have to do an integral all the time. It might just be sort of a difference type thing. But anyway, that's the definition. And this is technically T ds. So in other words, now I'm taking a step back from this for a second, just to say that the total energy is broken into two components called heat and work. Work is defined in work, and heat and work are what I was saying are like sort of I don't want to say abstract, but like you don't really get to control them very much. Like, we don't plot work anywhere, right? There's no plot with work and stuff. That's not a thing we normally do because they're not like basis variables. They're sort of derived from other things, right? We might use it because it's a useful thing practically, but heat and work are just sort of, they have units of energy, they're sort of abstract. They are both broken down in terms of two sort of real basis thermodynamic variables. Work is pressure and volume, right? Work is pressure times volume, right? If you take something at a constant pressure, we'll do an example after this. If you take something at a constant pressure and you change its volume, you've done some work, which is equal to P times delta V. And that's just from that thing with a constant P. And so work is literally just, as always, this is just F dot dx, but in 3 dimensions. So this work is just the same work we always do. This is just, we used this a long time ago from work energy theorem from kinematics. If you make it in 3 dimensions, then the force in all directions becomes essentially the pressure, and V, instead of dx for a linear force, you'd have dV for the whole volume form. So it's slightly different because this is like a vector and this is not. But anyway, it's roughly that's the rub. So I don't know where that came from. Anyway, so that's where work is. The other one, so this is like the master equation. I shouldn't have written that. I mean, this is true too, but like it's a little confusing because we don't need it right now. Let me write it like this because this is actually the true first law. And Q is the other one. Q is the other thermodynamic variable, and that is in terms of just like work can be broken down into pressure and volume, heat is broken down into temperature and entropy. Okay, so this is very hard to imagine. Why you're integrating over the entropy? Like, this is incredibly difficult to imagine because entropy is kind of a weird thing. But this is relatively easy to imagine, and what you should just think about is that, like, if you wanted to compute the work done and you know, let's say you had a constant pressure, then changing the volume just tells you sort of how much. Okay, I'm not going to say anything useful, I guess. What I mean is that this, you can kind of imagine why it means the work. You should just think of heat as sort of an abstract quantity. It's actually just like the work done by temperature against entropy. If that makes any sense. And if you don't, of course, that doesn't help because entropy is not.
Like whether or not the temperature is making more or less.
Exactly. Yeah, right. It's kind of like, it's like.
It's like an air conditioner, like you're either cooling it or heating it. Does that make sense?
Right, you're cooling or heating it, and that depends on the temperature, but it also depends on how you're changing the entropy.
Right.
Right, because if you're moving the entropy, of one system away from it, then you could be decreasing the heat. Anyway, you can see it's all like, I'm just saying words now. But anyway, the point is that these are both like, you should think of these as being very similar types of equations. It's just that this uses a weird thing, entropy. I mean, this is one, all right, well, I'm not going to get to it. There's a thing called an ensemble, which I'll just say what it is in case it's, what?
It's not just a band?
It's not just a band. It's even better. The ensemble means which variable you're actually doing the integral over.
Okay.
So have you heard of the microcanonical ensemble? The canonical ensemble?
I hadn't even heard of ensemble, so.
Okay. Well, the ensemble, so it's kind of a silly thing, because you might think, why did I write PdV and why didn't I write VdP? Like, you just might think, well, what if the pressure is changing? And that's actually true. This could happen. I mean, you could have, we'll show an example later. If you just draw a line in a different place, this you might actually want to use, and you could just use it and you'd be fine. But it doesn't seem like that much to worry about. But generally in these systems, you would choose which variable you're always going to be integrating over, and the other one is going to be a function. So P is going to be a function of V in this case, and T is going to be a function of S in this case. But if you switch it, you'd have it called a different ensemble. So the ensemble is, well anyway, sorry. It's sort of a side note that doesn't really matter. But, well, we'll talk about the microcanonical ensemble later when I talk about entropy. I'm writing this for myself later. We'll see. This is a very famous equation, by the way. probably, we'll talk about it. I think I should probably tell you what this means.
Okay.
This was written on a bridge somewhere in like England or something. Like a guy wrote it on a bridge. Boltzmann, I think. Actually, it might not have been Boltzmann. Someone wrote it on a bridge, carved it on a bridge because he thought it was so important. I think it's still there.
Was the bridge related to the equation, or?
No, he was on the bridge when he thought of it.
Oh.
And then I think it's on his grave now or something. Anyway, sorry. Let me just get back to this. So heat is given by TdS, but I also like saying TdS because it sounds like tedious. Anyway, because these forms are so tedious. Anyway, the important part though is that this, just like we can change this into P delta V if we want, if we knew that P was, let's say P was constant and V was just changing. In this case, we have, like, we can write it as T delta S. Yeah, we can write this as T delta S, that's it. And, right, okay, good, okay, sorry, for some reason I was confusing myself. Now, the change in the heat here and the heat here are, this Q hot, I could write, therefore, as T hot times the change in entropy during this phase. How do we know the entropy is changing during 1 to 2? We know it's changing because we know that this line is an adiabat. The lines are called adiabats, by the way. They're called isotherms. This is an adiabat, and clearly it's not continuous with this. So clearly the zero entropy line would go like higher. So clearly this is decreasing in entropy. Well, okay, it's changing entropy. I don't know if it's increasing or decreasing, but it's changing in entropy, right? And then this one down here, of course, is also changing entropy. So Q cold is going to be T cold times times delta S. Yeah. Oh, and sorry, okay, sorry. I should say the reason, how do I know these are the same delta S? I should have written like S hot minus S cold or whatever it is, right? But the reason we know they're the same is because this has a certain entropy. This is, if I call this S1, this is a constant entropy. So at this point, this is S, sorry, let me, how do I wanna? There's entropy S at S1 means at point 1, and S2, S3, and S4, right? Those are the 4 entropys at all the points. During Q hot, the entropy goes from S1 to S2. So I really should write Q hot is T hot times S2 minus S1, right? And then Q cold is T cold times, and it's going to be S3 or S4 minus S3 or something, right? But because we know these are adiabats, meaning they're constant entropy, S2 and S3 are the same, right? And S1 and S4 are the same. So I could actually write it, so what did I say? 1 and 4 are the same. So I could actually write this in 4, and 2 and 3 are the same. You know, whatever this is, 2. So essentially, this is, if I call this delta S, this is going to be actually minus delta F, sorry. Minus because the entropy goes back to, you know, the original one, right? So it was very important. So we used the fact that these ones are isothermal. We used that to, where did we use that? Oh yeah. Well, we used that to show that the heat was just given by this and this. And normally that would be very complicated because there'd be all these different entropies. But then we use these two to relate the 4 entropies we have at these 4 states to 2 entropies, because we actually only have 1 entropy here and 1 entropy here. Just like we have 1 temperature, a hot temperature and a cold temperature, we have a high entropy and a low entropy, right?
Oh, okay.
And in this case, we actually could do this whole problem without relying on, like this, it seems like of these 2 sides of this that we have heat and work, we haven't really talked about P and V at all in this. Like obviously they have P and V values. We haven't like used it at all. That's fine. You don't have to use them all, right? We've only used this side, which is the Q side. But that's fine because it works really well with isothermal things because the heat in an isotherm is always given by TH or T at that temperature times delta S always, right? For an isotherm. And that's another isotherm. And then the delta S, the entropy, can be related between these two things. So I kind of skipped a step. It's really this you should write first and then figure out that the S's are related. Anyway, now let's actually go back to this. If I plug in, let me move this out of the way a little bit. If I plug in Q cold is minus T I'm worried about a sign here. Maybe there's no sign here. I might have done one of these backwards. Oh, no, that's fine. Sorry. The reason there's no sign is because the Q cold is the heat that's leaving the system, right? Because you're always talking about the heat on the system. So the heat is actually leaving the system. So delta S is opposite of this delta S. So if this is the change entropy, this is the negative change entropy, but the heat from the system is leaving the system. This is the heat onto the system. This is negative heat leaving the system.
Right.
Well, it's heat leaving the system, therefore it's negative heat, but therefore these cancel and you get a positive number, okay?
Nice.
Exactly. So then we have 1 minus Q hot over Q cold. Let's just do it. Well, you see that these delta S's are going to cancel. And we just get T hot over T cold over T hot. And when you look at that, that's actually very simple, and it only depends on actual quantities here. We don't have to be like, well, like how much heat, because you can't really even measure. How are you going to measure the amount of heat we transferred? Like you'd have to like put like a thermometer that would warm up and capture the temperature, and then you could compute the heat, but then you'd have to, anyway, it would just be like, it's not easy to measure heat. These are infinite baths with just fixed external values. So this efficiency is given just in terms of those external things. It doesn't actually matter the values of the heat here. Efficiency only depends on these things. That's actually really cool. And actually, so what we can see is that, remember I said to have it be perfect efficiency, it's not just like an engineering problem. This is an ideal perfect system, okay? Obviously, it's perfect. When I say perfect, I mean that like these are perfect isotherms, and these are perfect adiabats, and these are perfect like infinite wells of heat, and when they give up heat, they don't reduce temperature at all. And this same thing, when they receive heat, it doesn't increase temperature at all. Even in this perfect example, the efficiency is not 1, it's 1 minus this ratio here. So how would you make this really, really efficient? You would have to make the cold one much, much colder than the hot one. If this is if this is absolute 0, and this is anything, then this would be exactly perfectly efficient. So you would need to be so if you're at any finite temperature, like if let's say your cold thing has to be, room temperature, and then they say, how do you make it more efficient? You literally just have to get your hot one to be like as hot as you possibly could, because this ratio needs to be small so that the efficiency is high. So this is called the Carnot efficiency, I think. Sometimes people just call it the heat cycle efficiency. And actually what's really cool, and I'll kind of spoil the ending for you a little bit, which is that I'll do another example of a heat engine faster, and which is the reason I want to do another example is because it's a little more complicated because there's an integral using that PDV integral. Anyway, it's not, and we have to use the ideal gas law, which we didn't really have to use here. But whatever, but you'll see that the efficiency of every heat engine is actually equal to the Carnot efficiency. And what this means is that if you have any cycle that makes a complete loop, because you've gone back to the original point, it's what's called a reversible cycle, right? It's reversible because all the entropy we've lost here, we've gained back on the other side. So it's perfect, it's completely reversible. right? And so and there's like a theorem or whatever, every reversible heat engine has the efficiency equal to the Carnot efficiency. They're sort of equivalent to the Carnot cycle. That makes sense? So in other words, we haven't really lost any entropy here. We actually have lost zero entropy, and the reason is because the heat that's gone to the cold. If you're really considering like your system as taking heat in and getting work out, some of the heat would be lost, and that would go into entropy over here. So you're actually increasing the entropy here and decreasing it here, right? And extracting work. So you are changing. It's not like you're violating anything, and you're not, But the reason that the inefficiency is dependent on this, it's dependent on this QC is because that's where sort of the entropy is going to. That's why you can't. So his example in class was, why can't you just like ice has a lower entropy than, to turn water into ice you extract heat, right? You have to, because ice is colder. So you extract heat. So why can't you just, in a boat, take water from the ocean and just freeze it and just take the heat and then dump the ice, right? And then you'd have heat now, and you could use that heat to do whatever, right? To, burn something, I don't know, whatever. And the reason you can't do that is because you'd be reducing the entropy, and you need to basically put it somewhere, and anywhere you put it would necessarily be basically using more energy. So it's like how do you actually freeze things? How would you basically? Okay, I'll say that again a little bit. If you actually wanted to do that, to freeze water and take the heat out of it, you would need to use a refrigerator. Or a freezer, I guess. That's literally the thing that he was talking about. An invention that would turn water into ice. That's called a freezer. And what a freezer does is it removes the heat from the inside of the freezer, but it of course does not actually just make the world colder, right? It pushes the heat outside, and to do that, it actually has to use a little more energy to even do that, because you're decreasing entropy in a box, and so therefore you're increasing it outside, and then that whole thing actually produces more heat. So anyway, so the point is that to even extract heat out of an object is not free. To extract heat, you can see, requires some dependence on entropy. It has to, So that's why you can't just take the heat from a hot thing and make it cold. Okay. And then I was going to do the Stirling cycle, which is just another cycle. We'll see. It looks very similar. But it uses slightly different equations, so that's why I wanted to do it. If you look it up on Wikipedia or whatever, heat engines or whatever, we know. So he mentioned that there's 4 types of lines you could have here that are interesting. Of course, you could have any line you want on any PV diagram. You could there's no rules. You could just draw whatever you want. But it would be really hard to compute unless you had something that was constant, basically. So each line on this diagram, this PV diagram, something has to be constant, right? If you just draw a random line, it's going to be, as I said, really hard to compute. So you could have, and normally there's 4 types. Yeah, he wrote a 5th one for no heat or something like that. But anyway, normally you have isocores. So an isocore looks like that. It's supposed to be vertical. An isocore has a constant volume. So this line so of course this is just telling you something that's happening to a gas. To make it a cycle, you have to actually obviously have it be closed. So I'm just drawing just a thing that would happen. This just means that you have, let's say it was this way, a gas at some pressure at a certain volume, and you make it lower pressure in the same volume. You have, of course, necessarily you have to change the temperature here. There's no way this would just happen by itself. You have to change the temperature, because otherwise, how would you lower the pressure if the volume was the same? You know what I mean? Anyway, this is called an isocore. Okay, then there's This one is called an isobar. The bar means pressure, right? Like the mil bar or whatever. I don't know what core is volume, I guess, whatever. Then we know that there's isotherms, which look like 1/x. And then there's the adiabats, which look sort of steeper, I guess. You could probably easily work out the equation, but I don't remember what it is. Anyway, some weird equation. And that's it. So those are basically the 4 types. And if you look up, this is what I was saying, if you look up the heat engine on Wikipedia, they'll literally list of heat engines. They're all named for some stupid person just listed another one. And they just say what happens at all 4 stages. And they literally, it'll be like, what if 1 to 4 was like an isobar? And what if 2, and they just make all the combinations, but they all named someone's, like, it's just like, well, yeah, it's like a combinatorics problem. Like, you just just list all the types. There's only 4 types of lines you could have, and there's 4 things, so just do it. It's like a choice problem. You could figure out, it's like 4 factorial, whatever it is. Like, you could figure out how many there are, but of course, every single one of them is named after a scientist. I'm just kidding. They're really smart people, but like, come on. It's like the Boyle's Law thing. I hate Boyle's Law. The thing that's like if you squeeze something, it gets smaller. Boyle's Law.
No
Genius.
shit.
Anyway, which is not even this whole thing. This captures all of those laws anyway.
Can't say anything, my name's not on anything.
Smart.
I'm off the grid.
There you go. So this is called the Stirling one. This is just a random other example. There's many other examples, but I just want to show you this one because, as I said, it's not that different, but yet the math is a little different enough that we should probably do it. The Stirling cycle has 3, 4 has 2 isotherms again. So actually these 2 are exactly the same as this one. This was an isotherm. But then the vertical components here, the 2 to 3 and 4 to 1 used to be adiabats, but now they're isocores. And so now before, the reason I'm putting these labels on is because what defines these lines? It's usually important to like say what defines the lines. Before, we had what defines the top and bottom lines were these temperatures, which is the same. What defined the other ones? Well, the entropy difference was the same in both. So we could sort of define the lines by this. What defines these lines? Well, because they're isocores, what defines them is, I'll call this V, well, I'll call this VB. I don't want to use numbers to confuse it, and then I'll call this VA. Right? So it's supposed to be just this. So from 4 to 1 and from 2 to 3, the volume is going to be constant, okay? So therefore we could write TH, TC, 2 to 3 is going to be VB, and 4 to 1 is going to be VA. So what I'm writing here is literally what is constant. That's kind of the whole thing. And now I'm actually going to write, so we could have done the last problem like this, what I'm about to do, but it was sort of a little too simple to do this, but this is often what you might want to do, which is write, which is write process 1 to 2, 2 to 3, so
Oh boy.
there's plenty. Things to write. So we're going to write here the change in energy, change in internal energy, heat, work. And the reason we need to do this, now last time it was a little easier because everything, there was like one thing that was like completely constant, like during the isotherms, during the adiabats, the heat there was no heat doing anything. And during the isotherms, there were no there was no change in internal energy. What else wasn't there? Anyway, the point is that it was a little simpler. Now we might have many of these things. And the point of finding the efficiency, the reason we're doing this is to find the efficiency. This is going to be the total work done divided by the total heat in. That's actually the real definition of efficiency. And for any heat engine, by the way, let me just actually substitute this in. For any heat engine, it's going to be Q in minus Q out over Q in. Like this is the same thing. And it's the same because we know that all a heat engine, remember that picture I was with the in, out, and work? That's always true for all heat engines. That's not just for the Carnot cycle. That's obviously a good example, but they're all, work is always equal to just Q in, Q out. That's conservation of energy. It's the only place. So you could also write the efficiency as this. These are equivalent. Now we might end up finding it easier to add up works in this thing. That's going to be just adding up these works, right? And Q total in is going to be adding up these Qs, but only the ones that go in. Right? The Qs that go out, that leave the system at the cold one, are not going to count. So, okay. So now we have to use a few of our laws of thermodynamics. Delta E is going to be CV delta T. Remember, M is not, we're not going to worry about it. It's just absorbed into C. This is the change in internal energy. This is the first law and the ideal gas change in internal energy thing all in one, right? I wrote it together. They're just separate equations, but we can just combine them because, I mean, they're not combined. They're just written next to each other. This is really important here because now we didn't have this delta E before because we didn't really need it because we just talked about Q and W, but they're related to each other by this. So in this case, it might actually be easier if we know delta E and we know W, we can just find Q. Because remember, Q has like the entropy and stuff in it. Entropy might be a little difficult in this case because nowhere is the entropy constant. So if we can avoid talking about entropy in this picture, because literally we have 4 values of the entropy, 1, 2, 3, 4, all different, but none of them are going to be the same. So if we want to avoid talking about entropy, and therefore we probably want to avoid computing heat directly, but based on the first law and the fact that we know that this is true for ideal gases, we can probably just find this column and just subtract them or add them or whatever and get this column, right? Does that make sense? Okay. Yeah. You could have also done this whole thing for the previous problem, obviously. Now, what's important is that delta E is the change in internal energy, is of course proportional to the change in temperature. During the isotherms, the change in temperature is 0. So during 1 to 2, that's 0, and during 3 to 4, that's 0. So that's actually already a huge thing. Already we don't. That's like really easy. Already we know that the work done and the heat in 1 to 2 and 3 to 4 must be equal, right? Because they're, as long as we get the signs right, they must be equal to each other, right? So that's huge. So all we need to do is compute one of these, like this one, and then we get this one, right? So, and actually, let's just fill in the other ones too. Delta E for here and here are just going to be, remember, this is at T hot and this is at T cold. And if this is this, delta E is just this, CV delta T. We can just write CV. Now, what did 2 to 3 go to? It went from T, hot minus T cold. And this is CV T cold minus T hot, or something. I might have the signs back. It doesn't really matter. I mean, it does matter, but I don't care.
Can we put that on the test?
You can try. I would not recommend it. It's just really annoying because according to the first, oh wait, sorry, I wrote this backwards.
I was actually going to ask you that, but I was like, no,
You would be
maybe
right.
I just messed it up.
It's Q minus W. Because W, again, is the work done. Now, of course, as I say every time, the signs are very important, but like the signs are only important if you know what these mean. Like you can get the signs quote unquote wrong, but if you just are consistent and you write, no, I mean W is the work done like on the system, which is actually minus W of this one. This is the work done by the system. So if you mean it the other way, you can actually write a plus and just, as long as you actually do it right, which I'm not guaranteeing that I'm going to do, then you'll be fine. So anyway, okay. So this is a change in internal energy. So actually this is the easiest one, even though it seemed like delta E was like a new thing on top of these two, and we'd have to figure out, it's actually easier. And then we'll see why that makes the other ones a little easier too. Now what about the heat? Okay, well actually let's look a couple of places. For this isocore, here's a great one. Okay, let's do this one. I know it seems like I'm kind of jumping around, but I'm just trying to do the easy ones first. This one here is an isochore, the volume is constant, and the pressure decreases. So what's happening is that you put, now it's always important, like as much as we go on this math little journey, on this little loop here, we should imagine what's the actual tank of gas that's actually we're studying is doing. In this case, it's in the hot bath, and then here it's being cooled down, and its pressure is decreasing, but it is not changing volume. So the piston is just stuck where it is, right? And it is just cooling, and therefore the pressure is normally it's very easy to think of pressure is dropping, right? Because pressure is going down, and therefore you think, oh, it's you're expanding it. It's not expanding, right? The pressure is dropping because the temperature is dropping. Okay, so work here is going to be it's integral P dV, but it's like P delta V. What's delta V here? 0, right? It's an isochore. The V is constant. So the work done is 0. And you can imagine, again, we're you don't want to get too lost in the variables. You just want to imagine how could you possibly get work done if the piston is not moving? Work literally is the piston's pushing against you. That's what work is. Work is you can lift something, you can whatever. How can you do that if it's stationary and it's not expanding? So whenever you have an isochore, whenever you have a vertical line here, if your volume is not changing, you can't possibly get any work out of it, right? So these are 0. So that's great. And now actually we know a few things because of these add up or subtract whatever to this. We know that this must be right? This is just the first law, delta E is equal to Q minus W. So therefore we know the heat transferred. So the heat transferred during this part and this part are just given by that. It's the same as delta E. And now what do we have to do? Well, there's 4 left, but as we saw, once we compute this, we have this one. Or this one, and then we have this one. Now, which one do you want to compute? Right, as we were saying, Q might be a little tough because entropy is not constant anywhere, and we don't want to do any integrals over S. That would be weird. Let's try W. It's probably easier for this one. What's W? The work done is integral P dV. That's the same as this. Just keep that in mind. It's exactly the same as this. It just might be easier to write delta if it's not, like if it's just a constant change or something. In this case, it's 0, so it's fine. But so this is P dV. Now we're computing this for 1 to 2. So what's the pressure? So we're computing the function that's the pressure change from 1 to 2 is what? As a function of volume, right? This work is integral P dV. Work done from 1 to 2 is integral of P1 to 2 dV. P1 to 2 now needs to be, this is an integral, right? P needs to be a function of V. That's how we do integrals, right? We need to write it as like a polynomial function or something of V. How would we do that? Well, what do we know about, this is 1 to 2, what do we know about this? 1 to 2 is an isotherm. So 1 to 2, we have PV equals, now we're going to use nRT. But this is nRT hot because it's at the hot place, right? So it's, this right-hand side is entirely a constant, right? So this is just a number. How do we get P as a function of V? Just like that.
That's not delta V.
No, this is for a single. This is for anywhere along this path.
Oh.
There's no changes
okay.
yet. This is at a single right. So I could pick like this point, and if I plug in my V, I should be able to find P.
I was thinking that because we were doing the 2 different.
Yeah, we
temperatures.
didn't integrate yet.
Yeah.
That's a very good question. We didn't integrate yet. This is actually anywhere along the path. Yeah. Now we have to do an integral. Well, what are the bounds of the integral? Well, the end is going to be at, the end is up here, right? So the beginning starts at VA, right? That's the beginning volume. We're integrating over V, so it's volume. The end volume is VB, and the function is P of V at 1 to 2, which is that, which is N, bless you, nRT H, which is a constant, so this can actually come out, but whatever, times dv over v, right? It was 1 over v and I just put it under the dv. So I should really write it. Sorry, I'll write it again. Right, it's like this. This is a constant, so obviously come out. Now this is an integral, right? It's a polynomial. I mean, it's not a polynomial. It's a inverse function thing. So what do we get? Well, what's the integral of dv over v? It would just be log, right? Natural log of v. And we have to plug in the limits again, so we get ln of vb minus ln of va, right? And just plug it all in at the top, minus, and plug it all at the end. But of course, by the rules of logs, we can actually write this as this. Right. So the sum of logs is just the product of their log of the product of their things, right? So this is just the division version. So there we go. This is work from 1 to 2. So you can see why it looks completely different than the other one. There's a log function in here, but it depends on the volumes. Those are input I mean, these are the variables that we knew about at the beginning, right? We could change any of these. We could just make something hotter. We could make this volume change bigger, like VB could be bigger, VA could be smaller, whatever. So everything in here is either a constant or one of those input variables. So that's excellent. So we're done. If we still had like a Q in here, that would be really annoying, right? Or a P in here. If we had a P in here, like if we left it like this, there's no P in here. P is not an input variable because P is never constant. So it'd be a little annoying to do that. So this is all in terms of, so this was work 1 to 2, that's this one. So this is nr t hot natural log of VB over VA. And now we know Q. Q must be minus, well, okay, I guess it should be the same as this. Right? Assuming I got my signs right. Q minus W is delta E, which is 0 in the first line. We know that those must be equal. Now, what's this one down here? No, we did this one. This should be very similar, should be the same. But of course, it's not. The only difference between this one we just did, 1 to 2, and 3 to 4, is that it's not T hot. Well, actually, that's one difference. Exactly. Also, the bounds of the integral are switched. Everything else is identical. This PV, so for 3 to 4, we just replace this with a C, PC, and we get the ideal gas law for the cold part. That's fine. And we also have to swap the bounds. So the only difference here is we get NR TC ln VA over VB. And now again, we can use the same thing, and this is just going to be identical. NR TC ln VA over VB. Well, great. Well, now we have a bunch of equations. So what do we do with this again? We want to calculate the efficiency, that's right. So the efficiency, where's my, oh, I put it back. Okay, does everyone follow how you fill in all these things? If you're not sure why we did all this, wait a second. If you're not sure how we did it, tell me now. I mean, it's no pressure, but okay. It just means these intervals and stuff. This is like the sort of the hardest interval we'll have to do in this section. So it's not like sometimes you'll have to do crazy, like you'll have to do trig sub or something. Like this type of integral is the hardest one. But and you can kind of see why is because this is like a linear equation, all these variables, meaning there's no squares, there's no sine, cosines. They're linear, and so the worst you'll have to do is divide by something and then integrate, and that's just log, right? So, okay, so I'll erase this. And now the efficiency, as we said, is the total work. Total work over the total heat in. We could also write this as the heat in minus heat out. Now, it turns out that there's a bunch of heats. So maybe we should go back to this one because there's some of the work is 0. Maybe that's a little easier. You could, of course, you could do either way, but I just wrote it down the other way. So we're gonna erase this one. Now, what's the total work done? Well, the work is only done here and here, right? And sorry. Also, I should have done this the other way. Just keep in mind that this argument is the inverse of this argument, right? And ln of okay, that's another thing. You could see that if you put x for the top line, it actually follows. So this is one of those things where, like, technically you only have to write like one rule of logs and you can derive all the other ones from it, which is kind of interesting. But if you, in the top line, if you put, actually, never mind. Okay, you probably could, but it would be a little hard. Anyway. Okay, so the point is that this is actually equal to minus nRTC ln of VB over VA, right? So if I wanted to, so the point is that the work total is going to be the sum of these two works, right? It's the total work done. And I'm going to actually get, now if I factor out, now this is something where you might need to write them all out, which is fine. Just nr, now I'm going to factor out nr, they're in the same. I'm going to actually do th minus tc because I'm going to flip the sign of this. And it'll be ln of, it'll be this one now, v over va. So I've just taken this bottom log of v over b and turned it into minus log of b over va. And therefore, if you add them together, then you just get that there's, of course, a minus sign now for the temperatures. Temperatures are different, so keep that in mind. It's very easy to think these are just exactly the same, but the temperatures are different, remember that. So that's the total work done. Now, what's the total Q in? So the Q in is, well, where did the heat go in? Well, actually, let's do one thing real quick. These two, as you can see, are actually going to cancel each other out. They're actually exactly minus each other, right? So the heat, this is the heat absorbed during 2 to 3. Yeah, so when it was at a constant, so basically when the volume didn't change and the pressure decreased because heat was radiated. On the other side, heat was absorbed, right? But these are actually exactly minuses of each other, you can see. So actually those are going to kind of cancel. I'm just saying when we're adding them. They don't cancel like physically they're different times that they happen. But if we're finding the total heat in, we know we don't have to worry about these because they're just going to cancel. However, these two, well, now remember, it's not actually going to, we're not going to necessarily add them together because when we had the other heat, and remember we had in the hot bath, you were getting heat, the QH for absorbed heat, and then QC for in the cold bath. And you don't want to count the heat it's radiating. You want to count only the heat it's absorbing, which is going to be this one, right? This is the heat it's giving off to the cold bath. That doesn't count. That's not the input heat. That's sort of leftover heat. This is the input heat that we care about. So we didn't even need to cross these out because we don't even care about them anyway. We only care about the input heat. Does that make sense? There's one caveat I'll get to in a second. HLN. And now, if we just figure out what this is, NR cancels. This is actually the same log, right? That cancels. And we get TH minus TC over TH, which is equal to 1 minus TC over TH. interesting. That's exactly the same as what we got before.
Very interesting.
See, this is the Carnot
I knew you were waiting for someone to reply to that.
Carnot efficiency.
Amazing.
But we have a Stirling engine. It's not the Carnot cycle. There were no adiabats here, and yet we still get the same efficiency. And again, the reason is it's the process is called invertible, and it's because if you have any closed circuit basically in this PV diagram with no sort of loss or whatever, like meaning it completes the cycle every time, you could always reverse it, right? There would be no, you're not losing any, if you. So one of the another way, I don't think we're ever going to use this, but you could also plot, this is a PV diagram, and we seem to, like every time we think about them, because it's very easy to think, oh, compresses and then it expands and then it pushes and whatever, right? But you could also draw all of these heat engines. You could do this whole chapter of the book could be in terms of TS diagrams, which is this whole separate one, which is where now the Carnot cycle would actually be a square. Because remember, in the Carnot cycle, we had isotherm and then adiabat. And then, right, isotherms are now straight lines in this TS, and adiabats are now vertical lines. So as you can see, and now what would this be? I don't know, something else. But like, you could see that you could actually do them all in here. And the only reason we really use this, PV versus TS, is, well, two reasons. One is because no one's super comfortable with S entropy. Even after a while, I think most people are like, I don't really know. P and V are like, it squeezes and it's small. Like that's the whole PV, right? It's very easy to understand. It's very easy to understand what's happening when you let something expand and when you press. And then it's easy to even imagine what the temperature is going to be like. We knew how to plot these, but in this case, to find. Actually, there's three reasons. The other reason, second reason. Actually, I forgot the third reason now.
Second reason.
Well, I'm not going to number them. Another reason is that there's no S in here, right? You could write this in terms of S if you'd like. You can. But we usually do it in terms of PV and T. You don't actually need all the variables. It's kind of like an overdetermined. It's like how in an isothermal problem, P and V are there's only one variable. Because if you give P, you can find V. Because everything else is a constant. So it's kind of the same thing. It's there's too many variables, and we usually leave out S from this equation. You'd have to like rearrange a little bit if you want to get S into it. But you could put ST equals NR V or something. I mean, it wouldn't be that. It would be something else. But it would be like something that looks like that with S and T. It's just that we don't usually use S for those things. I forgot the other reason. Oh, because of work. Because the main thing we care about with these are engines. An engine gives you work. That's the whole point, right? We don't care about heat. We don't really care about, we don't want to get heat. We don't need that. We need work to be done. It's not like I'm rallying like a communist party sort of.
Work.
Yeah. So anyway, the work is what's important. And here in PV, work is literally equal to integral of P dV. So you can see that in this case, if you take the integral over P dV in this closed loop is going to be actually the area of this region here. Now, it's very hard to find here, but if you had, like, let's say a square diagram, that would just be a fine cycle. It would just be iso cores and iso bars. We could work that out. It would be a little more complicated because you'd have a bunch of logs everywhere. Because during the other ones, you'd have V equals and P over here, and you have to integrate. It would basically be the same thing, but like a little more annoying. But if you had that, you could actually literally take the area of the square, right, just length times width, and that would be equal to the amount of work done. It would be delta P times delta V or whatever, right? Yeah, and so that you could just find the total amount of work done by the system. So if they gave you, actually that would be interesting if they, well, it would be a little hard. I was just going to say, if they just gave you in a PV diagram a box, and they told you to find the efficiency, this you don't even have to do any work to get. You could just take the area of the box. So it would be, if this is, P2, P1, and V1, V2, it would be P2 minus P1 times V2 minus V1. That would literally be work total. Now, obviously, then you have to find Q in, which is very complicated here because there's no constant temperatures or constant entropy. So it'll be a little hard. But anyway, so that's another reason. The area of this is the heat, but we don't, as usual, we don't actually care that much about the heat. But anyway, so just I think if you had to know a few facts, like word sentence facts as opposed to math facts about this topic, it would be that the Carnot cycle. It'd be how to do the Carnot cycle. If someone says compute the efficiency, you should be able to write it all out. You shouldn't just memorize it, obviously. You should be able to, like, step by step write it all out. This one is obviously, you should be able to do, but like it's a little harder, obviously. But you should at least know that the math tricks are to write these three variables as opposed to just Q and W. You don't think you would need delta E because you don't think, it doesn't come up in any of these equations. But it turns out it's massively helpful because of the first law and because of the, MCAT law or whatever it's called. Equipartition theorem, I guess, is the actual technical name. And then, anyway, and so it makes it much easier. And then, well, what was I going to say? And then the Stirling cycle, and basically the other cycles, all have the same efficiency as the Carnot efficiency. And it's the efficiency of a reversible heat engine. That's it. The reason I drew this at all is to show that the entropy is not, you're not losing entropy when you go around the cycle. You're getting right back to where you were. You're at a high entropy, low, and then you went back to high. So this is reversible. The only way it wouldn't be reversible is if you didn't have a circuit that completed if it decayed or did something weird, which you won't have anywhere. But yeah. And then the last thing I was going to say was, I forgot. Anyway. And maybe I already said it. Who knows? Okay, anyway, does anyone have any questions about this? So this is heat engines. You can look up equations. So this table here, if you look up, there's a place somewhere online and in books and stuff that lists for every possible thing, like an isotherm, isochore, isobar, adiabat, it lists the actual answer for all of them. I would not recommend looking at that because it'll literally tell you these, but it'll it's just way too much information, and it's like you're supposed to it's just an integral. It's just an integral. You can, I don't know. It looks like you're supposed to memorize something, and you're clearly not supposed to memorize anything. So I'm not a huge fan of those. But those you can check your answers with those. But I would not try to write all that on your paper for the test because I actually think you will be confused by it. Because it'll be this term, and then it'll be another term with pressures, and you'll just have to know that in this one we're not using pressure as anyway. It's the whole thing. So yeah. And then of course they could ask you a question that's after you do all this, they could ask you what's the efficiency if TC is if the heat baths are 300 Kelvin and 1,000 Kelvin. You just plug it in. It's, whatever 70%. I think it's 70%. Or they could ask, what would you do to make it more efficient? And you could say change the temperature, whatever. But yeah. Oh, sorry. That's right. The other thing I was going to say is the thing I erased, which is this. Okay, so I'll talk about this. This is completely unrelated. It's same S, but it's not the same thing. Which is, what is actual entropy as what's the definition, right? Yeah, we have it in terms of Q is TS and all that stuff, but what actually is entropy on? Okay, here's where I'm going to mention again for probably the last time the ensembles. What we've been using now is called the canonical ensemble. The canonical ensemble means that we use volume for the horizontal axis and entropy for the horizontal axis. So we define entropy as, well, you can define entropy as the like derivative of heat with respect to temperature if you want. That's kind of I wouldn't do it that way, but that's kind of the definitions that you would take the heat over temperature, and this would be equal to the entropy, just like you could take the work over the volume, and this would be the pressure. So this is called, this definition of entropy, which is not a very helpful one. This is equivalent to just saying Q is T ds, right? Because it's just by the, fundamental theorem of the calculus, whatever it's called. So anyway, this is one definition of entropy. It's like the relation between heat and work. Just like what if you could define pressure? So this is like here. You could define pressure as you change the volume, how much work do you get out of it, right? How much work do you get out of the volume changing? You could say that's the pressure. But we know that pressure is actually like force per unit area, right? We don't seem to be referring to force per unit area anywhere here. We're not actually talking about molecules hitting a thing. This is the canonical ensemble. If we go back to talking about molecules, right, and looking at configurations of molecules and molecules hitting a thing in forces per unit area, that's called the microcanonical ensemble. All that means is that, are we talking about molecules or are we talking about differential equations? Of course, they're supposed to be the same, but you sort of need to, it's basically like what type of system are you talking about? It could be the same system, but in one case you're saying I have a set of molecules with average kinetic energies, blah, blah, blah. In one case you're saying I have thermodynamic variables that relate to each other in these equations. That's it. So if you're confused why entropy seems to pop up in random places, they're all the same. It's all the same entropy. It's just that sometimes you're actually talking about the configurations and the disorder, and sometimes you're talking about this. Just like with pressure, sometimes you're talking about the thing that you have to integrate over the volume to get the work. But sometimes you're talking about force per unit area of molecules hitting a thing. Is any of this helpful?
Sorry,
So the only reason I bring up any of this is because in the microcanonical ensemble, we have, this is the definition of entropy. So I think this was the one on the bridge, and I think this might have been in the slides. What this means is that this isn't constant, so don't worry about it. This log omega, this is actually natural log, but the one on the bridge, he writes a log, that's why I write like this. Every time they write log, they mean natural log, basically. I don't think anyone ever, after 10th grade, ever means log base 10. I mean, I don't know, maybe you guys had used it or something, but I've never heard of anyone meaning log base 10 anytime after like 10th grade. Anyway, this is called this is like the number of microstates, it's called. That's why we're in the microcanonical ensemble. So remember how he was saying you have a box of gas and you have like all the gas kind of in the corner of the room. Like if you had a real box of gas, there's no real reason why all the molecules couldn't just be in the corner of the room sometimes. Like they're random, right? They're all going at random angles and things. Why couldn't they all just bunch up to the corner of the room for a second? Right? They totally could. But I think I was saying last time, sort of qualitatively, how many states have that type of behavior? How many states of the total number of states you could have? And of course, technically there's an infinite number because there's sort of a continuum, but let's just say we're going to quantize it. We're going to go to like the quantum world where everything can have where in the bands we had to like divide them using the uncertainty principle. Let's just say we have like every atom can have a finite position. There's like a grid. It can be in one spot on the grid. It can have some velocity that's like an integer, right? So now it's all finite, okay? That's basically an approximation of the world anyway, so it's fine. Or it might really be the world, but that's a whole separate subject. But why couldn't you have, that's a finite number of states. What if you wanted to say, how many states have all of them? So this is my grid of, obviously I'm not really doing a very good job, but like every box can have a gas atom in it, right? And they sort of have random velocity stuff. What are the chances that all of them are in this corner? Well, you could just count, if you were patient enough, you could literally count and do a combinatorics problem to figure out what percentage of the states had all the gas molecules in this corner, and just say how big you want the corner to be, whatever, right? You would find that it's a very small percentage, and therefore you would find that this number omega is the number of states with that configuration. So let's say I only want them to be in the corner, but of course they could be. You could mix them up, and that would be the same state. So it'd be like two states with the same configuration, or they could be rearranged but just in the same corner. That would be the same state. So if you take these are called microstates. A microstate is an actual snapshot of where the things are. Okay. If you mix them up a little bit, but you want to say of all, what's the entropy of the configuration where they're all in the corner? I don't actually care about like where exactly they are, but like I want them all to be in this region. You would just count the number of microstates, meaning the number of snapshots that have that property. So how many snapshots have them all in the corner? Then you take the log of that number. It's a big number, obviously. Take the log of that number as a constant, and you get the entropy of that configuration. Okay. Then, sorry, just one more thing. And then if you're taking the gas is randomly distributed in the room, now you have to say what that means, but like that just means that that there's no region where there's like no big region where there's no molecules. Count the number of microstates with that property, and do that. You'll get a much, much, much larger entropy. And so what this means is that if entropy tends to increase, then if you start your gas in a configuration that has very few microstates, it will tend to go, so this statement, increases what I meant. This is the second law of thermodynamics, right? Well, what this means is that what this means in the microcanonical ensemble means that your system will tend to go towards configurations where there's a lot of multiple copies that look very similar. So if all the gas molecules in this area, there's many configurations where I would just say, they're just basically everywhere. There's very, very few, comparatively, that are all in one corner. Effectively, there's like zero, right? Of course, there's some. You could just put them all in the corner, that would be fine. But there's very, very few. So the idea is if you start them all in the corner, they will tend to fill the room, and they will tend to never go back there. Because what you're doing is you're saying, I'm going from a configuration where there's very few microstates to a configuration where there's a lot more microstates. And just the only difference between numbers of microstates and entropy is just the fact that you take the log. There's reasons why that's true, but whatever. It just means it's roughly proportional, right? Log is like an increasing function. So basically, the more microstates there are, you'll likely find yourself in the future in a configuration that has more microstates than in the past. And that's this statement. That's the second law. Yeah, sorry. What were you saying?
No, I can't tell if you're saying that it's impossible for all the gas to go in the corner of the room, or if it's just so unlikely it wouldn't happen.
It's just so unlikely it wouldn't happen.
So there's a chance.
There is a chance, because if I said it wouldn't happen, that would mean that there's a physical law preventing it.
Okay. That clarifies it then.
Yeah, all it's saying is just that it's literally a statement about random things. It doesn't have even anything to do with physics. It's just the idea that like if you configure a bunch of random events, what are the chances that they'll all, if you roll 100 dice, what are the chances? Oh, that's actually okay. Why didn't I say that before? That's a much better example. Dice. If you have a bucket of dice and you can shake it up and then they'll all land, you can see all of them. A microstate is a value of each of the dice. So you have 100. So a microstate would be if you say die 1 is that it has a 6, and die 2 has a 4, and die 3. That you'd label all of them. They're all different. That's called a microstate, a value for all of them. You shake it up, that's a single microstate. So every time you shake it, you get one microstate. But what class, we tend to care about, like, let's say all the microstates where there's about equal numbers of each, of 1 through 6. There's a lot of those microstates. There's exactly one microstate where they're all equal to 2. So the idea that if you started them as all 2s, because you can start them in any microstate you want, and then you shook it up, you would expect it never to get back to 2, right? And that's what that's saying is that your entropy is just increasing. You're going towards, every time you shake it up, you're still getting exactly 1. Each microstate is equally likely. The one that's all 2s is just as likely as the one where this one is a 6 and this one is a 4 and this one is a, right? They're all equally likely. It's just that we don't usually care about those distinctions because the class we're considering, where it looks random, quote unquote, where you look at it and you're like, it looks random, that is such a big set of microstates that the entropy of that state is much, much higher. So it would tend to become more like those states if you shake it up. Does that make sense? So I'm just trying to get you to see that it's not like there's a mysterious new variable called S that only comes up in thermo and then you think about it for a second. Like it's just basically a statement about like random things. It's just the idea that when you shake up a if you have a random thing that you don't know the details about, obviously it's not really random. The dice have kinematics and you could solve for things, but effectively it's random on this scale. Then they will tend to just they'll tend to land on configurations that are most likely, which is like kind of a sort of dumb statement. It's like, yeah, sure, that's what most likely means. And with actual gases in rooms, most likely states would be ones where the gas is basically uniformly distributed. Even though each state is equally unlikely, they all have the exact same probability of happening. There's just way more where they look, where you would call it uniformly distributed. So therefore, they're more likely. And all that whole story can be captured with a variable called entropy. That's the whole thing. And therefore written as a law. Because you can't just say that, in general, you have to like write it mathematically as a law, which is literally there's this statement. That's it. And that's why in the fridge, when you cool down things in a fridge, you are decreasing the entropy in the fridge because you're selecting that the molecules with higher kinetic energies basically have to either give up their kinetic energy or leave the fridge, right? So you're actually decreasing the entropy inside the fridge, right? You're selecting the microstates of gas inside the fridge are only cold air molecules. There's no hot ones. That's a very unlikely thing that wouldn't happen just in the world, right? Because entropy. So that's why in the fridge, of course, you have to pump the heat out, and you're actually increasing the heat. You're actually moving the heat outside the fridge, and therefore the heat is contributing to the atmosphere and actually increasing the entropy of the world. Anyway, that's it.
So by that
Fiction.
logic, if you could figure out a way to get negative energy,
Negative energy.
negative energy, like get below 0 Kelvin.
Okay, negative temperature.
Yeah, negative temperatures corresponds to negative energy, right? Like a prediction of the 3 laws.
Why don't you finish your idea, and then I'll see what I want to question you on.
No, I was just wondering if you could get to a cold enough level such that all life on Earth would just freeze completely and stop. Wouldn't that effectively be saying the same thing as you'd be stopping time because you're
I
stopping
knew
the
this
flow
was
of
going to be
energy?
good.
Yeah, it would be interesting, right?
Yes, actually, so that kind of actually relates to the third law a little bit. The third law of thermodynamics is that entropy, that there's basically in the micro version, the entropy of the state, there's exactly one minimum entropy state. So if every single particle is in its lowest energy state, there's only one place that could happen, right? Because there's imagine like every atom has all of its electrons in the lowest state, but it had 0 temperature, like it didn't even have thermal energy. Everything was at 0 temperature. Everything would be, there was exactly one microstate. So omega would equal 1. This is at T equals 0 Kelvin. There is one lowest energy microstate. It's actually not 0 energy because of it's a thing, we didn't do it, but the quantum harmonic oscillator. We kind of did it with the square well, right? The square well, the lowest energy didn't have 0 energy, right? We showed that you couldn't, that's not normalizable. The lowest was, n squared, whatever it was, pi, whatever. So it had some non-zero energy. So that would be the lowest. So it's not zero energy, but you couldn't go any lower. So it's the lowest possible state. There is one microstate, one configuration where that's the case. What if we plug in 1 here? We get S is, what's the log of 1? 0. Right? Because log of x is y means that e to the y is x. So log of 1 would be e to the what is 0. Sorry, e to the what is 1. E to the 0 is 1, right? So S is 0. So that means that the entropy is actually equal to 0. So it's not like one of these things with energy where like potential energy and all these energies, usually you can scale them and they don't have a 0 value. They just have like, you can just add every, potential energy. You can just add a constant to all the energies and it's fine. The only thing that matters is the difference. This is not like that, which is actually kind of weird. Actually, it's not that weird because temperature has the same thing, has a 0 value. Volume, I guess, never mind, it's not weird anymore. Volume is the same thing. There's a 0 volume. There's a 0 pressure. Okay, never mind, it's not weird. But energy has that property. Energy can be scaled up and down, doesn't really matter. But entropy, we've found, has a 0 value, and it happens only when I realize I don't want to say a long sentence, but it happens only when you're in a state where there's exactly one configuration. And the only time that could ever possibly happen is when you're at 0 Kelvin. Or you're just, if you're in like a really small, like if you're at 1 atom, okay, maybe that would be a little different. But like if you're in a real big system, the only possible way that you could be in a state with only one, that you would have only one configuration of all the molecules in the room is if you're at absolute 0 and everything was in the lowest possible energy state. So this is the second law. So we did the whole first problem with the first law. That's just delta E. That's just saying that thermodynamic energy is composed of work and heat. Work is made of pressure and volume, and heat is made of temperature and entropy. That's the first law. The second law is this statement, which is just that more probable configurations that have more possibilities, it will be in more often. That's fine. This is the third law, which is this here, which is that at 0 Kelvin, there is exactly one microstate that things can be in, and therefore the entropy has to be 0 there. That's it. So the 3 laws.
For 12.6, while you're on the laws, where it's saying like air conditioners and refrigerators, it's talking about the second law, it doesn't violate it because it's putting more entropy out into the world?
Yeah.
Okay.
Yeah, in the room, it's decreasing the entropy. That is true.
Right. But like it's not getting rid of it, it's just
Exactly.
putting it somewhere else.
Right. So the room is not a isolated system, is the point.
Okay.
It is a closed system.
No, it is not closed. Oh,
Like a
yeah, I guess it is.
freezer is like a closed system, right? I mean, like
I-
not perfectly, but
Sure.
so in like you're saying it heats up the world, therefore.
Okay,
increases
you could say they're
entropy in
both
the
closed, I
world.
guess. Because an air conditioner, I don't think blows in outside air, does it?
It can.
Maybe it
It's
does.
like a
Anyway,
combination.
let's just. A freezer doesn't, obviously. A freezer does not. Yeah, freezer doesn't take in outside air, right? It just cools the air in it. For that example, yes, it's a closed system because gas cannot flow in or out,
Right.
but it is not an isolated system.
Okay.
And the statement is that this increases in an isolated system. I didn't even finish it, sorry. Isolated system. There's all these like caveats to all these rules, but they're not like silly like they're actually really important because of that. So S does decrease inside parts of systems. You could
So-
have that.
Okay, so disregarding what it said originally, it doesn't violate the second because it's not an isolated system.
You can answer it 2 ways. You could say the room, just the inside of the room that's
Mhm.
being cooled, is not an isolated system,
Right.
so therefore it doesn't apply.
Right.
And / you could say that if you took the actual true system, the full system, you would include the outside.
Okay.
In that system, entropy is increasing.
Okay.
Or being,
If you
it's
consider
not, but
like the world an isolated system or something, you'd say it isn't violating it
Yeah, you could say that.
replacing, moving the entropy.
Exactly. You could talk about the whole work. Yeah, sure. That's fine. Yeah. I'm just thinking about like energy going into space or something, but
Okay, well, I tried.
the universe.
All right, the universe is
said
an
the universe-
isolating system.
Energy is not leaving and entering the universe. We know that for sure.
Okay. My fridge in my apartment is
It's not sending
to the
energy out of the universe.
All right.
I have a couple homework questions.
Sure. I have not looked at them.
Okay, well, I'm kind of stuck. Let's look at, so 12, 18, and 22. I don't know if you just want to read them and
What's 12? Do you want to? Yeah. How about? Can you read it?
consider.
Is that really long?
Yeah.
Oh. Okay.
No, it's not
There
really.
you go.
Considering 3-centimeter column of mercury inside a glass tube, 0.1
Mhm.
radius, how much mercury would the column move
Oh, I see.
with the bulk expansion? I'm just confused on how you set that up. So this is how I kind of set it up, but I was confused because looking at the problem in the book,
Yeah.
it gives you two different radiuses. So that's kind of how
Mm-hmm.
I looked at that problem. The problem in the book is on page 225. If you wanted to. The
Oh,
mercury from
225.
is like the problem, like an example.
Yeah. Oh, okay. Because I was gonna say I want the formula for. Yeah. So.
So that one's a little kind of different.
Right.
I'm kind of stuck.
Well, so we know the volume, right?
3 centimeters.
So if it's so if the column. Okay, we'll do this. So this is 3 centimeters,
Radius is 0.1
and the radius is 0.1
millimeter.
millimeters. Sorry. So we can find the volume of the mercury, right? We would just do the volume that's already in there, not the change, but the volume that's already in there is pi r squared h, right? Wait, you have to obviously change the units, but
Wait, it says the area of a column of mercury is AR2 squared. Well, I guess R, so it just, there's no H in this problem down here. But they give the example. Oh, but it says, never mind. This translates to a change in column height, delta T, volume over. Yes, then you would be right. It's like the very last sentence on the page.
on the next page.
No, the first one.
The transition change. Oh, I see. Yeah. Right. So sure. So the
So that would be the volume then.
yeah, right. The change. So once we find the change in volume, if we divide that by the area, we'll get the change in height. I mean, that's just how things in closed-in cylinders will work like this, right? So this will be pi r squared down here. So we need to basically now to find delta D, which is the problem, right? That's the problem. We need to find delta V, right? But delta.
So how much would the mercury move? Column move, yeah. So that
Yeah.
would be delta T.
Delta D, yeah.
D, sorry.
And now we have to just use their.
But the change in volume, there wouldn't be there would there?
They told us beta, which is a number,
Yeah.
and that's equal to.
Oh, so we can plug in our volume and then it's delta V equals VO V delta T.
Yeah. I think. Sorry, I didn't visualize that properly. Yeah. Okay, it's right here. It's at right before that problem. It says delta V is V naught
So V naught
beta
would
delta
be
T.
the V that we previously found.
Yeah, this is V naught. Right, this is V naught. That's it.
So that's the formula.
Yeah, so we're given these parameters.
Mhm.
We know that this is mercury, so we can find the volume of the mercury initially, which is this.
Okay.
And then what we want is, we know that, of course, if we have a change in volume, what we actually want to measure, we can't really measure the change in volume directly, but we can measure the change in height, which is going to be delta D, and that comes from when it's fuller, this amount up here is delta V, right? The sort of amount above this. And so the amount is related because it's in a cylinder through the area of the cylinder, which is pi r squared. So therefore, now we've reduced the problem to finding delta V using what we were given, which is this, and beta for mercury, which is a value with units of inverse temperature. Something.
Now, delta T, it doesn't say anything about change in temperature in the problem. So what will we use for delta T?
How much would the mercury column move in millimeters per degree Celsius, given the mercury has a book expansion? You could use 1 degree Celsius, because it says they want your answer in millimeters per degree Celsius.
Oh,
So this means
okay,
per
so
1 degree.
Okay.
Yeah, yeah, yeah. So
change in delta T.
I mean, technically, if you wanted to like really be careful about the units, you could say that this is equal to, and delta V, we actually want delta V over delta T is technically what we want, right? Which is equal to V naught times beta. And then we'll get delta D over delta T. And this will actually be millimeters per degree Celsius. So that you could do it that way if you want to, but or you could just plug in 1. I mean, it's the same thing.
Cool.
So,
Put in 1 here, it's the same. Yeah.
Awesome.
so you're saying that the area of a circle is equal to change in volume over change in diameter.
The area of a circle.
So if you were to swap delta D and pi r squared, you get delta V over delta D is equal to pi r squared.
Yes.
It makes sense. I've just never seen that relationship before.
In a cylinder? Yeah, the volume and height is related through just the area of the circle, right?
Okay.
Because if you add like a gallon of water or whatever, how much height does it go up? Well, it just spreads it over the area
I see.
and then fills it up into another. It's just another cylinder, right? This is technically, if you move this over, this is technically the volume of this top cylinder up here,
Oh, I see.
right? It's not the volume of the whole thing. It's just but it's still a cylinder, right? If you pour more things on top of something in a tube, it's going to make a cylinder. So yeah.
Okay, that makes sense.
Yeah.
Cool.
Maybe I'm confused.
Yeah.
The second part of that, it says, remember that the radius of the column as well as the length will increase with temperature the same alpha. Now,
Oh.
Part B, you're changing the expansion coefficient, sure, but you're only changing the expansion coefficient of the mercury. They don't tell you anything about the glass.
Wait, how much would your interchange if using the linear equation of expansion of gas is alpha?
Sure, yeah, just swap out and compare. Swap out the constant and compare, but the radius of the column as well as its length will increase.
I think they mean
God,
mercury.
Are you in a
what an
cone?
awful.
You're not
That's
in a
stupid problem.
cylinder then. If your radius is changing, you're in a cone.
I think they're just saying that all parameters of the glass, all lengths of glass, what are the lengths of glass? R and H are the only lengths of glass, right? And D. Yeah. All lengths of glass are, this is not a sentence, are going to have the property that looks like this, which is going to be delta L over L naught is alpha now, delta T. So it's sort of like a Young's modulus. This is like a Young's modulus thing. But they're just saying that this is the same as this, right? But I just wrote it in a better way. And they're just saying that if all lengths of glass have this relation and the alpha has units of something per degree Celsius, right? And delta T is, you could put it to be 1 again because they want everything per degree Celsius. This has to be true for R and H. So it means that we also have to have, I'll write it over here. We also have to have delta R is R naught alpha delta T, and delta H is H naught alpha delta T, and okay. And now we just need to find delta D again, but our cylinder, hold on. Now V naught is actually going to be the same, right? Because the volume of the mercury didn't change. So that's actually good. So this we don't have to compute again. But this one will change because now we have, okay, delta, we're going to have this, but R is not going to be R anymore. It's actually going to be R naught. It's our previous R plus delta R, right? So I should put not here, but just like our previous R plus delta R squared is going to be, that's it. We don't actually need this at all, actually. Because it doesn't matter what the original height was, right? Oh, well, hold on. Did they ask what the final height is, or did they ask how much it goes up?
How much would your answer change if you just swapped out? Oh, I'm sorry.
It
It's
just
a linear
says-
coefficient. Yeah.
Well, it just says how much would it move.
Math.
In part A, it says how much would the mercury column move. It doesn't say the final height. So the fact that we had 3 centimeters, this actually is no longer going to be 3 centimeters because as the glass expands, the same volume of mercury is going to be there, but it's going to be it's going to be lower because it's going to be like in a bigger area. So this H is actually going to be not 3 centimeters anymore. So that's why I was wondering if they wanted your answer as the total height, but they did not ask. If they did ask for that, we'd have to recompute this with H plus delta H and R plus delta R.
I thought they were asking to swap the expansion coefficient of the mercury.
No.
That's not
Use
what they're
both.
asking. Okay,
So
yeah.
use this same thing, everything's the same. Yeah, everything's the same, except R, the radius here. Basically, all that's changing is that the cylinder, I'm exaggerating by a lot, obviously. The cylinder, the glass has gotten bigger, right, and longer, but who cares about that? And so therefore, the same volume of mercury now is lower. So this is slightly less than 3. We could compute it if we'd like, but we don't need to. And so now, if you increase the temperature, we know that the volume changes by a certain amount of the mercury still. That's the same, we just did that. But now it fills a wider radius. It fills a pool with a radius of R plus delta R.
Okay, so if you were measuring with this and you're putting graduations on it, now that it's a different, the hotter it gets, the closer those graduations become.
Yes.
Okay.
Yes, but it also gets longer. So they actually get farther apart. Like if you put lines on it, then you heat it up, the lines themselves will move. You're saying if it was
You're
hotter,
increasing the radius.
you increase the radius, but you're also stretching it lengthwise too. That doesn't happen to matter for this problem because we didn't care about the total length.
Right.
Because this amount, it doesn't matter what it's in,
I'm
but
trying to understand it.
this is a really annoying problem. But I believe that the fact that the length changes doesn't affect us at all because there's no point where we actually care about the actual length of the glass anywhere.
So all we need to do is focus on delta V is equal to V naught times beta times delta T, and shouldn't have an impact on the correct answer.
The change in volume should be the same
Okay.
of the mercury, but it will correspond to a different height change because the glass is now bigger.
Okay.
it's sort of wider
So then where do those two formulas about delta L come into play?
on the
And
left
delta R.
side all over there. That's delta R.
Okay.
So this is true for any of the properties of the glass. Oh, sorry, this is your book. Okay. Anything else?
Quick question for
Yes.
18. Do you have the buffer for me?
I did. Sorry.
It's got
Yeah.
the arrows next to it for
The
this.
Yes,
equation
oh, okay.
here would just be delta S equals M L over T. No.
Let me look at it.
Maybe not the solid state.
Takes 80 calories per gram to melt ice at 0 to water. That's the latent heat of fusion. Okay. 1 gram of ice has a volume of and the process amount decreased by. Does the liquid have more entropy than the solid state? How much does the entropy change at atmospheric pressure? That's strange. So, I think they want you to use a specific heat. Is that what you said?
Yes. I think.
There's a. Sure, no, okay. Yeah, so S is equal to S at some temperature. Oh, right. There's no change in temperature.
No.
Huh.
That's why I'm
Yeah, I see. Well, that is a tough one. Is that the last one?
Nope, it's
Oh.
18. There's number 22, but I just didn't
Perfect.
know much at 22, so.
Okay. Well, hopefully it's the hardest one.
It gets worse.
I'm not sure. So what do we have? We have M, we have V,
So we have the volume and we have the calories. And
yeah,
yeah, so it's 1 gram.
oh, maybe,
And then it gives you pressure.
yeah, that's also confused me a little bit because somehow you have to use volume here, and I'm not sure where you'd use it.
Or is it there?
I'm gonna, let me just write some. That's not right. Maybe something like this, but I don't know. How about I will come up with something to say on Monday.
Okay.
Sorry, I don't know.
It's a weird problem.
Yes. It's because I was just looking in the book. It doesn't seem like there's like an example that's similar. I assume it's something to do with you want to use this rule for. This is true for entropy. It's a differential change in entropy
Yeah.
is equal to dq over t, right? And you can integrate this, and you get the total entropy at some. Well, in this case, you get the change in entropy
Mm-hmm.
over this
Yeah.
region, and somehow they want you to use Q, the heat. I guess you could find the heat from the latent heat of fusion times the mass, right?
Yeah, that's what I was thinking.
And then I guess you could do that, and then you'd plug in the temperature, which would be the same in both cases, but the heat would be I'm not sure. Because I'm just the whole thing about this is like I don't know where you'd use V.
Wait, wouldn't they?
This is not. I don't write this.
They-
It's true. We're saying if
Oh, you
internal
don't think
energy.
that's there. Okay.
I just
So
read-
That's what I did.
Oh, you wrote what I.
I did delta S equals ML over T.
Delta S equals ML. Okay,
So
yeah.
kind of what you. Yeah.
Oh, that's what you said before. Yeah. Yes.
But then it would be the.
That would tell you the change in entropy. That would tell you how much more entropy water has than ice.
Correct.
So it seems like that would be fine, but what does volume have to do with it, and then what does pressure have to do with it? That's why I suspect that.
Does the liquid state have more than the solid state? So that would answer the first problem, right? The first question.
Does the liquid state have more
than the-
entropy?
Yeah, than the solid state.
I mean, I think so.
So
I
that
don't see why it
equation
wouldn't.
would answer then the first.
Yeah,
But then it's how much does the entropy change at the
that's what I'm really. I'm
Yeah,
not
that part I
thrilled
don't
by
get.
is the pressure, because I don't know what the pressure has to do with. These are not gases, so I'm not sure what the.
point of putting it.
I mean, I get that, of course, by freezing and melting, you're responding to changes in. That's a change in volume.
Yeah.
And so therefore, you're pushing against the atmosphere or being pushed by the atmosphere. So that is some kind of work, but you wouldn't. You can't. We don't know how to write that in. There's no ideal gas law for ice. Like. So anyway, there's probably easier than I'm making it sound. So I'll look it up and come to you. Hopefully on the Monday office hours, I'll do like all the homework problems.
Hopefully.
Hopefully, I mean, because I've already done a few, right?
Yeah.
So hopefully there's.
You gotta do Thursday? Is it due Thursday?
Oh, due Thursday. Yeah, I think
When's
so.
a 7 due?
After
Does
spring
he
break.
do?
Oh,
break.
7.
Oh, it is.
Yeah.
Yeah.
He was 7.
There's one due next week, right?
Yeah.
That's,
So
Yes.
this is 6 is due this coming week.
yes,
And then
on
7 is
Thursday.
due the week after.
No, that's spring break, so it's
Okay.
the week
so
after that.
the
Yeah.
week after that. Okay.
Oh, so this is due Thursday next week?
Yes.
Oh.
Yes.
The homework that we're talking about now is due the next Thursday that will occur.
Okay.
I didn't know that. That was
I don't know
Tuesday.
why I say it like that, but yeah.
The next Thursday that will.
The next time it is, you can say today's Thursday, you'd be correct. That is when it's due.
I think I'm just gonna say that the pressure has nothing to do with it.
Well, I don't know about that. Because it might, and it's just a little more subtle. I'll come up with, first of all, I'll figure out the answer, but then second of all, I'll figure out a good way to say it.
Huh.
All right.